If a human can see it, so should your system. Reliability requirements for machine vision components. Thank you. Talk a little bit about what this actually means, why it's important, what are the risks, and what is this paper trying to achieve. So currently there is a huge absence of detailed, exact criteria outlining how these machine vision components should perform. And what are machine vision components? These exist everywhere, in autonomous cars, to surgical robots, to classification systems, to the Ring doorbell that you might have that can tell you when somebody walks up to it. Um, and so there are no requirements that define how these systems should respond when there are changes or distortions to visual inputs, um, variations such as lighting, blurriness, or noise. And without these standards, without these precise requirements, developers and stakeholders have different interpretation of what constitutes as acceptable or reliable performance, leading into inconsistencies in how these models are made and evaluated. So this leads a lot into the risks because these systems are used widely. Ensuring the reliability, at least in the case of autonomous cars, is to prevent accidents and ensure safety. So what this paper is trying to do ultimately is to present a systematic approach to defining what the baseline for these machine vision components should be. And that baseline is based on human visual performance. How well does a human do? And that should be the standard for what these machine vision components should live up to. Ultimately, this leads into why we should care. Of course, safety concerns are there. A big one is the human versus machine perception. Again, humans are able to detect, maneuver, and work around different conditions, visual conditions, be it different lighting conditions, be it raining, fog. We do get impaired, but there is a certain degree of performance that is still there. And so we want to be able to measure this on how a human does it and versus a machine does it. And lastly, regulatory and ethical implications. We'll talk specifically about autonomous cars in this example. And for autonomous cars, it's very important to determine what is the baseline that is required for these systems before they're deployed worldwide. Is a human performance enough? Is some arbitrary metric one that we should be looking at? And in the case of this paper, they present that the baseline for any of these systems should be, again, how a human performs. So let's look at some of the key contributions that this paper brought forth on a high level. Firstly, they define two different metrics, the correctness preservation metric and the prediction preservation. What the correctness means is, for a given image, do we label it or identify it correctly? The prediction preservation is very similar. It's to say that if we had an original image and an altered image, and they both convey the same information, but there are just slight transformations on them, then the predictions for both of those should be consistent. Based on this, they defined this visual change metric as well. And so this is a metric to quantify the visual changes in images based on human perception. So this was a mathematical formula, just essentially highlighting how different are two images based on a human's perception of them. To be able to get this metric, what they did was they did an empirical study with over 2,000 people, labeling different images, variations within them, measuring the differences. And based on this, they were able to get a distribution that they use this visual change metric. And lastly, what they did was they spent an extensive amount of time talking about the reusability of this data that they collected and how it could be applied not to just the same domain or different objective, but across domains and across different objectives for different machine vision components. So let's talk a little bit about what is this visual change and how do they measure it. It's done through two different assessments. One is the VSNR, which is the visual signal to noise ratio, and the VIF, the visual information fidelity. The first one checks if the images are perceptible to humans. Does this image convey the information that it needs to for the label that it has? And this could apply to different altered images as well. So, for an example, it could be if we have a car in a particular setting and we increase the brightness on that image and then increase the brightness again some more on that image, is the third alteration still perceptible to humans? What is the degree of change between the third image and the original image? That's what the VSNR is calculating. The VIF, on the other end, is calculating something very similar, but it's checking how much of that information is preserved. So the difference between the original and the third image, we want to check how much of the original information is still retained in the third one. This is a very important metric because then it could be used to create new images on the fly that are within the distributions of what humans are expected to be able to see and that are outside the distribution of humans. And essentially the purpose of this is to standardize a visual change correlating with human perception. And so with enough data, you can have a consistent application of this across different transformations and images and be able to quantify how well a human sees and then be able to generate new images outside of that realm and within that realm. So a very concrete example on this, we can look at the triplet of images here. So we have the original car, then we have a brightened up car, and then we have a somewhat more brightened up car. And so this is transformations that have been applied onto the original image. And so using ResNet 50, we can see that it's still able to classify this as a car across all the three images. For the second example, for B, that's not the case, but it's consistent. It wasn't able to identify the original as a car, and it still wasn't able to identify the second and the third as cars either. But on the last example, what's odd about this is that the double brightened image is recognized as a car, whereas the original wasn't. This isn't aligned with human perception, so this is a gap in the reliability. Cool. So the approach that they took, and this paper also focused on autonomous cars, is that they took and identified what are the likely transformations that are going to occur in real-world scenarios. And for them, that they found was brightness changes captured, day to night, blur captured different environmental conditions, the cameras being dirty, there being fog, there being overcast, and then noise, which could be through rain, occlusions, spottings on the camera as well. And then what they did was they wanted to measure the visual change. They have this large gathering of data, and they want to calculate what the VIF and the VSNR was going to be. In order to calculate this, what they need is humans to label this data. And so this is where their metrics came in, which is how correct is something and what is the prediction preservation of this. So as you can see for ImageNet on the side, they did a couple of transformations, RGB changes, contrast changes, defocus, blur, and frost. And for that, they calculated, using the 2,000 humans, how often they got it correct. And based on different changes that were applied to this, how often were the same labels given to the original image on the altered images. And based on this data is actually very important and can be applied to to learn a distribution of what RGB levels can a human perceive. And so from this, they were able to, get their requirements, the prediction preservation and the correctness preservation that should be maintained for any transformation that occurs. So the research questions that ultimately this paper was trying to answer is, do human tolerated ranges of transformations depend on specific image sets, or can they be generalized? And so what they found on this was that these ranges are consistent across different image subsets and transformations as well. And so this is very important for the generalizability of this approach. And the confidence intervals that they found for various subsets were similar at the end of the day, and suggest that similar ranges can be reused across different image sets, even the ones that are not directly used in this data, in this experiment. Second question was how do existing robustness evaluation methods compare to human tolerated ranges? And so what they found was um, in traditional methods, transformations like brightness and frost are not captured by current benchmarks. And they found that their benchmarks, because they identified real world transformations, cover a wider range of images that humans can tolerate that MVCs are currently lacking in. And in their sense, they provide a more comprehensive evaluation of robustness. And lastly, where they're asking, can their reliability requirements identify weaknesses that are not detected by existing benchmarks? Like the second question, and that's a resounding yes. They are able to detect weaknesses that are not currently captured by current benchmarks. Cool. And then lastly, some discussion questions to think on and ponder upon. Is this a practical way to implement these requirements industry wide? Should regulatory bodies mandate testing MVCs against human tolerated ranges? Should the benchmark actually be somewhat higher than what humans perform at? Um, Likely, should we aim higher than human performance ultimately? And what are the implications of deploying less than perfect machine vision components in safety applications? Thank you. That was the end of the presentation for the paper